For most of human history, a profound silence echoed across our perception of the cosmos, not the silence of space itself, but the quiet of our own minds, unprepared for a specific kind of violence from above. This celestial deafness persisted, even when the universe roared. Our understanding of the greatest threats from beyond Earth was shrouded not by darkness, but by a peculiar lack of imagination. To truly grasp this cognitive gap, we must journey back to the morning of June 30th, 1908, to the remote Siberian taiga. On that ordinary day, in a landscape where nomadic Ivanki reindeer herders lived their ancient lives, an unprecedented cataclysm erupted from the sky. A searing fireball, brighter than the sun, tore through the atmosphere, followed by a shockwave that flattened an estimated 80 million trees across 2,000 square kilometers, an area roughly the size of a modern major city, like London. The blast, later estimated to be equivalent to a major nuclear weapon, specifically 15 megatons of TNT, was felt hundreds of kilometers away. Windows shattered in distant towns, and seismic stations across Europe registered the tremors. Yet, for nearly 2 decades, the global scientific community largely ignored this colossal event. This was not a mystery of what had occurred, but rather a profound question of why it was so comprehensively overlooked. In an age of emerging global communication, a phenomenon of this magnitude failed to register as an extraterrestrial threat. Instead, it was widely dismissed as nothing more than a peculiar meteorological or seismic anomaly. Initial reports from the local Ivanki witnesses, who spoke of a great thunder and trees falling like matchsticks, were largely treated as folklore, the tales of an isolated indigenous people, rather than empirical observations of a truly alien impact. The very idea of a random, catastrophic impact from a small, unseen body simply had no category within the scientific paradigm of the early 20th century. This was an era confident in a predictable, almost clockwork solar system, where celestial mechanics were seen as orderly and immutable. The cosmos, in this view, was not a chaotic shooting gallery, but a grand, harmonious machine. This deeply ingrained terrestrial bias prevented scientists from even conceiving of such an external, unpredictable danger. They looked at the sky, but did not truly see the dynamic, sometimes violent, nature of its inhabitants. It was not until 1927, almost 20 years after the explosion, that the first serious scientific expedition finally reached the Tunguska site. Led by the Russian mineralogist Leonid Kulik, this tireless team faced immense logistical challenges just to access the remote epicenter. Kulik's meticulous work, revealing the radial pattern of the flattened forest and the absence of an impact crater, pointed towards an atmospheric explosion. Yet, despite his groundbreaking findings, Kulik's work remained largely unknown outside the Soviet Union, further contributing to this great silence. This narrative of delayed reaction serves as a powerful metaphor for humanity's historical celestial deafness, a condition born from a critical lack of both the necessary technology and, more importantly, the mental framework required to even process such a threat. The true significance of Tunguska, therefore, lies not in the explosion itself, but in the human failure to immediately comprehend its origin and implications. Our understanding of the universe, it reveals, is profoundly limited by our inherent terrestrial biases and pre-existing expectations. The threat from space is as much a story about the evolution of human consciousness and perception as it is about astrophysics. It was a failure of imagination, a fundamental inability to look beyond our own immediate world, long before it was a failure of observation. This silence persisted, a quiet denial of cosmic reality, only to finally begin to dissipate when our own terrestrial conflicts and the terrifying weapons they spawned inadvertently forced us to look at the sky with new and much more fearful eyes. What if the greatest danger lies not in what we can see, but in what our minds, for centuries, were simply unable to perceive? What if the universe has been screaming a warning, yet humanity, in its intellectual evolution, has been largely deaf to the message? Our journey into the true nature of killer asteroids is as much a story of astrophysics as it is a profound exploration of human consciousness and how our worldview shaped, and often distorted, our understanding of cosmic threats. For countless millennia, when a blazing comet or a falling star tore through the night sky, it was not seen as a physical object, a rock from space, but rather as a celestial whisper from the gods. These were divine omens, powerful messages etched in fire, interpreted by priests, shamans, and astrologers who held sway over kings and commoners alike. A comet might foretell the fall of an empire, a plague, or the birth of a hero, but never was it considered a piece of cosmic debris that could physically shatter a civilization. This ancient worldview, steeped in mysticism and fatalism, inherently precluded any genuine scientific inquiry into the true nature of these transient celestial visitors, effectively creating humanity's first profound celestial blind spot. Then came the Age of Enlightenment, a revolutionary era that championed reason, empirical observation, and the systematic understanding of the natural world. It was a time of intellectual liberation, but paradoxically, it forged a new, equally pervasive form of blindness regarding the heavens. Propelled by the groundbreaking work of Isaac Newton, the cosmos came to be seen as a perfectly orderly, divinely wound clockwork universe, a grand mechanism of predictable precision. Planets orbited in harmonious ellipses, stars were fixed beacons, and the very idea of chaotic, world-altering debris raining down from the heavens was not only deemed unscientific, but almost blasphemous. Such a notion was a regressive throwback, considered a primitive superstition utterly incompatible with the elegant, predictable design of the Newtonian cosmos. The space between the planets was presumed to be an empty, pristine void, a clean stage for celestial ballets, not a shooting gallery. Into this rigid scientific orthodoxy stepped a German physicist named Ernst Chladni, a man whose observations and radical ideas in the late 1700s would forever alter our perception of the sky, even if he first faced ridicule. In 1794, Chladni published a groundbreaking book, a meticulous treatise that dared to argue the unthinkable. Meteorites, those strange, heavy stones occasionally found embedded in the earth, were not terrestrial rocks struck by lightning or volcanic ejecta, but rather genuine stones that fell from space itself. His claim was met with vicious derision by the established scientific elite of Europe, including the highly influential French Academy of Sciences, which dismissed his theories as the ravings of a madman. Chladni, however, was no charlatan. He was a pioneering investigator. He painstakingly gathered meticulous evidence, interviewing eyewitnesses who described fireballs and sonic booms accompanying the fall of these stones, and conducting early chemical analyses that revealed their unique metallic compositions, distinctly different from earthly rocks. He pointed to the commonalities among meteorites found in disparate locations, arguing for a common extraterrestrial origin. Yet, despite this compelling, almost overwhelming body of evidence, his work was summarily rejected, not because it was flawed, but because it simply did not fit the prevailing paradigm of an empty, orderly space between planets. The very idea challenged the comforting predictability of the clockwork universe, and the scientific community, resistant to chaos, chose to remain blind to the obvious. For centuries, humanity was not merely lacking the technology to detect extraterrestrial threats. We were fundamentally unequipped, intellectually and psychologically, to even process the evidence right in front of us. We had to laboriously unlearn the ingrained idea of a perfect cosmos, a divinely ordained, unchanging celestial sphere, to begin to truly understand the real, messy, and dynamically violent nature of the universe we inhabit. This historical bias, this long-standing celestial blind spot, continues to echo in our modern understanding, manifesting in the subtle ways our brains are wired. Cognitive psychology reveals that we are inherently prone to underestimating low-probability, high-impact events. A 1 in a million chance of a catastrophe often registers as practically zero in the human mind, even when the consequences are civilization-ending. This psychological phenomenon, a remnant of our ancient inability to perceive the cosmic threat, continues to challenge public and political engagement with the asteroid threat even today, making it difficult to galvanize the sustained will and resources needed to face an unseen enemy. In the terrifying crucible of the Cold War, as humanity teetered on the brink of self-annihilation, an extraordinary, almost miraculous, irony unfolded. Billions of dollars and countless hours of human ingenuity were poured into developing tools of destruction and deterrence, systems designed to detect and prevent nuclear catastrophe. Yet within this intense geopolitical tension, these very instruments of war inadvertently became humanity's first true planetary defense system, revealing a threat from beyond Earth that had remained largely unseen or stubbornly ignored for millennia. Our journey into understanding killer asteroids takes a sharp, unexpected turn, from the depths of human conflict to the farthest reaches of our solar system. At the heart of this accidental awakening was a groundbreaking United States program launched in the 1960s, the Vela Hotel satellites. These orbital sentinels were designed with a singular, grim mission: to police the Partial Test Ban Treaty of 1963. Their task was to vigilantly scan for the unambiguous signature of an atmospheric nuclear detonation, a telltale double flash of light that would betray any clandestine atomic test by a rival nation. Orbiting high above, these sophisticated spacecraft were the ultimate silent watchmen, their electronic eyes scanning the globe for any flicker of forbidden fire. However, as engineers and analysts meticulously sifted through the continuous streams of data flowing from these highly classified satellites, they began to notice something profoundly unexpected. Amidst the expected background noise and the occasional anomaly, a pattern emerged: frequent, powerful flashes of light that bore the unmistakable characteristics of massive explosions, yet they were not from Soviet bombs. These powerful bursts, each one equivalent in energy to a small atomic weapon, were, in fact, the signatures of large meteoroids entering Earth's atmosphere at hypersonic speeds and violently disintegrating in a spectacular airburst. It was a cosmic fireworks display, completely unbeknownst to the world below. For decades, this remarkable data remained shrouded in the highest levels of military classification. It was a secret byproduct of nuclear surveillance, an unacknowledged and unintended gift from the Cold War arms race. This hidden trove of information represented the first systematic, truly global survey of asteroid impacts on Earth, silently accumulating proof that our planet was far from a quiet, protected sanctuary. This clandestine catalog of cosmic bombardment was growing, year after year, yet it was accessible only to a select few within the intelligence community, its implications for planetary defense completely unrealized by the wider scientific world. Then, in the early 1990s, as the Cold War waned and the geopolitical landscape shifted dramatically, a profound shockwave rippled through the small, often marginalized community of astronomers who had long been struggling to convince the world of the very real threat of cosmic impacts. The decades of classified Vela data were declassified, suddenly revealing a startling truth. Impacts on the scale of a small atomic bomb were not rare, once-in-a-century events, but were occurring several times a year, across the globe. This was hard evidence, undeniable and irrefutable, painting a picture of a solar system far more dynamic and dangerous than most had ever dared to imagine. It was a revelation that irrevocably shifted the paradigm, finally giving credence to the warnings that had, for so long, been dismissed as mere speculation. This remarkable story highlights the crucial role of interdisciplinary cross-pollination, a phenomenon where technology designed for one purpose unexpectedly revolutionizes an entirely different field. A military technology born from the urgent need to monitor terrestrial conflicts and deter nuclear war completely transformed the nascent field of asteroid impact studies, providing the empirical data that astronomers had so desperately needed. It was an unforeseen convergence of fear and discovery, where the drive for planetary security from human threats inadvertently unveiled a much older, cosmic danger. The Vela satellites were not the only accidental watchmen. Other military systems, like the early warning systems for intercontinental ballistic missiles known as the Defense Support Program, or DSP, also inadvertently contributed to this secret catalog of Earth's bombardment. Designed to detect the fiery plumes of ascending ICBMs, these incredibly sensitive infrared sensors also picked up the heat signatures of incoming cosmic objects, further solidifying the evidence that our planet was under constant, albeit mostly harmless, assault from space. These powerful systems, built to protect humanity from itself, became the unintended eyes and ears that finally allowed us to truly perceive the cosmic danger lurking in our own solar system. This profound awareness of a celestial threat was, therefore, not born from pure astronomical curiosity or a sudden enlightened understanding of the universe, but rather emerged as a direct and profoundly ironic consequence of humanity's own deeply ingrained, self-destructive tendencies. After millennia of celestial blindness, then decades of accidental discovery, a stark reality emerged. Our planet is a target in a cosmic shooting gallery. But merely knowing the threat exists changes little if we cannot understand it. How then? do we investigate a billion-year-old suspect, millions of miles away, armed with only light and radio waves? We cannot send a detective to dust for fingerprints on a chunk of rock traveling at tens of thousands of kilometers per hour. Instead, we must transform the remote science of astronomy into a fascinating forensic investigation, using ingenious techniques to build a detailed profile of a potentially hazardous asteroid. We move far beyond simply finding faint dots of light moving across the night sky. Those initial sightings are just the first step, akin to finding a suspicious shadow. To truly assess the danger, we need to know what that shadow is. Is it a dense, metallic cannonball, a fragile, dusty snowball, or a loosely bound collection of rubble, barely holding itself together? The answers to these questions are absolutely critical, because they dictate the entire strategy for any potential mission to nudge or deflect it from a collision course with Earth. One of our most powerful tools in this cosmic crime scene investigation is spectroscopy. Think of it as truly universal fingerprinting. When sunlight strikes an asteroid, different materials absorb and reflect light at specific wavelengths, creating a unique spectral signature. By analyzing this light, split into its constituent colors like a prism revealing a rainbow, astronomers can deduce an asteroid's precise chemical composition. Is it rich in iron and nickel, suggesting a solid, dense core of a shattered protoplanet? Or is it primarily made of carbon, indicating a more primitive body, potentially carrying water ice and the complex organic building blocks of life itself? This distinction is paramount. Hitting a solid iron asteroid might be like striking a bowling ball, but impacting a loose pile of gravel could be like punching a beanbag, potentially breaking it into multiple, still dangerous fragments, turning one bullet into a shotgun blast. Then there is the formidable power of radar astronomy. For decades, facilities like the now-lost Arecibo Observatory in Puerto Rico, with its colossal 305-meter-wide dish nestled in a natural sinkhole, acted as a cosmic sonar system. By beaming powerful radio waves across millions of miles of space and listening for the faint echoes that bounced back, Arecibo could do far more than just detect an asteroid. It could ping these distant objects, creating detailed three-dimensional images that revealed their precise shape, their exact size down to mere meters, how fast they were rotating, and even if they had tiny moons of their own orbiting them. These radar maps were like taking a high-resolution photograph of a suspect's face from a distance, revealing every pockmark and contour, allowing scientists to understand its rotation and stability, crucial information for any future interception. But asteroids are not always predictable, simple billiard balls moving through space under the sole influence of gravity. They have hidden accomplices, subtle non-gravitational forces that can, over decades, subtly alter their paths. One such force is the Yarkovsky effect, a concept first developed by the Polish-Russian civil engineer Ivan Yarkovsky around 1900, long before the space age began. It sounds like science fiction, but it is pure physics. As an asteroid spins, the sun's energy heats its surface. This heat is not radiated uniformly back into space. As the warmer side cools and radiates more thermal energy, it produces a minuscule, almost imperceptible push, a tiny jet of heat. Over short periods, this push is negligible, but over decades, or even centuries, this continuous, gentle nudge can cause an asteroid's orbit to slowly but significantly drift, transforming what was once a near miss into a direct hit with our planet. It is like trying to push a mountain with a feather, but doing it continuously for 1,000,000 years. Yet, even with all our remote observations and clever deductions, there is no substitute for physical evidence. Just as a forensic team collects samples at a crime scene, humanity has begun sending robotic emissaries to collect fragments of these ancient wanderers. Recent missions like the United States OSIRIS-RX, which visited asteroid Bennu, and Japan's Hayabusa 2, which journeyed to asteroid Ryugu, represent groundbreaking case studies in evidence collection. These spacecraft didn't just observe, they landed, collected samples of regolith and dust, and then embarked on the long journey back to Earth, delivering pristine pieces of these cosmic bodies to laboratories. Physically retrieving these samples allows us to ground truth our remote observations, confirming what spectroscopy and radar told us, and often revealing completely new and unexpected details about their composition, internal structure, and the deep history of our solar system's most ancient and potentially dangerous inhabitants. These tiny fragments, some no larger than a grain of sand, hold within them billions of years of cosmic history, offering unprecedented insights into the very earliest days of our solar system and the true nature of the rocks that still wander its vast, dynamic expanse. The image etched in our minds of an asteroid impact is often a singular, apocalyptic crater, a world-ending cataclysm. But the true danger is far more insidious, a threat that ripples outward in ways we are only just beginning to comprehend. The physical blast is merely the opening act. The real drama unfolds in the chaotic, far-reaching consequences that would sweep through our deeply interconnected global systems, challenging the very fabric of civilization and the delicate balance of life itself. We must look beyond the immediate devastation to understand the second-order effects, the profound disruptions that even a moderate, non-extinction level event could unleash. Consider a stark scenario. What if an event of Tunguska's magnitude, a 15-megaton airburst equivalent to a very large nuclear weapon, occurred not over the desolate Siberian taiga, but directly above one of the world's critical agricultural breadbaskets? Imagine the blast unfolding over the vast, fertile plains of the American Midwest, or the rich, dark soil of Ukraine. The initial shockwave would flatten crops for hundreds of square kilometers, decimating a harvest that feeds millions. But the immediate destruction is just the start. The colossal amount of dust and debris lofted into the atmosphere would, even from an airburst, partially obscure the sun, triggering a localized yet severe climate disruption. This effect, though temporary, could be enough to cause widespread crop failures far beyond the immediate blast zone, extending across entire regions or even continents. Modern economic modeling and supply chain theory paint a grim picture of the subsequent domino effect. Global food production would instantly plummet, sending commodity prices soaring to unprecedented levels. This spike in food prices would trigger market crashes, shattering national economies and plunging vulnerable populations into widespread famine. Nations, desperate to secure dwindling resources, would face intense geopolitical instability, leading to potential conflicts over food, water, and arable land. What begins as a purely physical impact, a force from space, rapidly transforms into a socio-economic and political crisis of unparalleled scale, challenging every aspect of our globalized society. Yet, the economic tremors are only one facet of this complex threat. A profoundly fascinating and perhaps unsettling biological question emerges when we consider what happens to a specific type of cosmic visitor, a carbonaceous asteroid. These ancient space rocks are not merely inert chunks of stone. They are often rich in complex organic compounds and, crucially, water ice. When such a body disintegrates in our upper atmosphere, shedding material in an airburst or a series of smaller fragments, it introduces a sudden, massive influx of alien chemistry into our biosphere. Scientists are engaged in an ongoing debate about whether such events, even if the risk is considered low, could introduce novel extraterrestrial molecules or even extremophilic organisms into Earth's biosphere. This concept, known as panspermia, suggests that life, or its building blocks, could travel through space and seed new worlds. While the risk of a true space plague might be minimal, the unpredictable ecological consequences of seeding our planet with a sudden infusion of alien chemistry are far from understood. Such an event could potentially trigger harmful algal blooms in the oceans, disrupting marine ecosystems and suffocating aquatic life, or initiate other unforeseen environmental chain reactions. It is a biological wildcard, a reminder that the universe is far more complex than we can often conceive. The implications are clear. The greatest danger posed by a moderate asteroid impact may not be the immediate crater it creates, or the shockwave that flattens buildings. It is the intricate and fragile web of civilization and biology that the shockwave would ripple through, exposing every weakness in our food systems, our economies, and our delicate planetary ecology. Our continued existence, therefore, depends not just on tracking these celestial wanderers, but on understanding the cascading effects they could unleash upon our interconnected world. We have peered into the cosmic darkness, deciphering the silent warnings of a universe far more dynamic than once believed. We have begun to read the ancient fingerprints of incoming threats, learning their composition, their trajectory, their subtle dance through the solar system. But knowing a mountain is on a collision course with your home is merely the first terrifying step. The true monumental challenge lies in moving that mountain, and here humanity faces a series of profound paradoxes that test not just our engineering prowess, but the very fiber of our ethical and political will. Consider the recent Double Asteroid Redirection Test, or DART, mission by NASA. This ambitious endeavor saw a spacecraft, roughly the size of a small car, intentionally crash into Dimorphos, a small moonlet orbiting the larger asteroid Didymos, millions of miles from Earth. The impact, traveling at 22,500 kilometers per hour, was designed to slightly alter Dimorphos's orbital period, and it worked. The orbit shifted by over 30 minutes, a testament to human ingenuity. But to see this as a final victory, or even a complete solution, would be a dangerous illusion. DART was not the last word in planetary defense. It was merely the very first sentence in a long, complex, and as yet largely unwritten instruction manual for saving our world. The first, and perhaps most immediate paradox we confront is the rubble pile problem. We often picture asteroids as solid chunks of rock, dense and unyielding, but many are not. Spectroscopy and radar astronomy have revealed that a significant number of these cosmic wanderers are loose agglomerations of gravel, boulders, and dust, held together by nothing more than their own weak gravity, like a cosmic beanbag or a pile of cosmic debris. This presents an enormous engineering conundrum. Striking such an object with a kinetic impactor, as DART did, might not deflect it cleanly. Instead, it could be like punching that beanbag, absorbing the impact without significant redirection, or, far worse, shattering the asteroid into multiple, still dangerous pieces. One bullet, intended to neutralize a single threat, could suddenly become a shotgun blast of dozens of lethal fragments, each one a potential catastrophe, turning a solvable problem into a nightmare scenario. This stark reality pushes us to consider more elegant, though undeniably more technologically demanding, solutions. One such concept is the gravity tractor. This method foregoes brute force entirely. Instead, a spacecraft would fly alongside a hazardous asteroid, perhaps for years, using only its own minuscule gravitational pull to gently, incrementally, tug the asteroid onto a new, safe trajectory. Think of it not as a punch, but as an invisible, celestial hand guiding the asteroid away, inch by agonizing inch, over vast spans of time. The forces involved are tiny, almost imperceptible on a human scale, but applied consistently over months and years, they can accumulate to shift an object weighing billions of tons by thousands of miles. This method, while requiring unprecedented precision and endurance from our spacecraft, carries no risk of breaking the asteroid apart, offering a clean, controlled deflection. But even if we perfect the engineering, an even greater challenge looms: the immense geopolitical paradox. Who holds the authority to make the decision to deflect an asteroid? Consider a future scenario. We detect an asteroid with a 99.9% probability of impacting a major city in one country, guaranteeing millions of casualties. Our calculations show we can deflect it, shifting its trajectory by just a fraction of a degree. But that precise shift, while saving one nation, might create a new, tiny, say, 0.1%, risk of it impacting a completely different nation years or even decades later. Which country gets to make that call? What if the nation facing the guaranteed impact demands action, while the nation facing the newly introduced tiny risk refuses to be put in harm's way? There is no international framework, no global body, no universal law currently equipped to adjudicate such an unprecedented ethical dilemma. This problem quickly transcends the realm of rocket science, plunging us headfirst into the complex waters of international law, ethics, and global governance. Finally, there is the most insidious paradox of all, the paradox of time. The easiest asteroids to deflect are the ones we find decades, even a century, in advance. A gentle, persistent nudge applied far from Earth when the asteroid is still millions of miles away requires far less energy and carries far less risk than a desperate, last-minute intervention. But this requires a sustained, multi-generational commitment of funding, resources, and public focus for a threat that may not materialize in our lifetimes, or even in the lifetimes of our children's children. How do you justify billions of dollars every year for a threat that might never come? How do you maintain political will when the immediate crises of today always seem more urgent than a potential cosmic catastrophe decades into the future? This fundamental challenge runs directly counter to short-term political cycles, economic pressures, and the human tendency to prioritize immediate gratification over long-term existential planning. After deciphering the cosmic chaos, after mapping the unseen dangers, a deeper, more profound question emerges. It is a question that eclipses all others, forcing us to look not just at the stars, but inward at ourselves. What truly is our ultimate place in the universe? For millennia, humanity has been a passenger on a fragile, blue vessel, adrift in a vast, indifferent ocean of space, constantly bombarded by unseen forces. Our journey through the science of killer asteroids reveals far more than just rocks hurtling through the void. It uncovers a mirror, reflecting our own evolving consciousness and our burgeoning role in the grand cosmic narrative. Consider this remarkable truth. For 4.5 billion years, the Earth has endured the random violence of the cosmos, a target in a celestial shooting gallery. Dinosaurs vanished, vast oceans boiled, and entire epochs of life were extinguished by impacts from space. Yet, through all that time, there was no conscious entity, no species with the foresight or the capacity to intervene. Now, for the very first time in our planet's immense history, a species has emerged that is not only aware of this existential threat, but is actively developing the extraordinary capacity to consciously intervene in the very cosmic mechanics of our solar system. This is an unparalleled moment, a pivotal turning point not just for humanity, but for all life on Earth. This awakening to our cosmic vulnerability and our potential cosmic agency compels us to embrace a new, profound responsibility. As thinkers like the legendary Carl Sagan so eloquently articulated, planetary defense is not merely an insurance policy, a mundane task of risk management. It is instead a fundamental obligation of a sentient technological species. It is a sign of our coming of age on a cosmic scale, a declaration that we are no longer just passive inhabitants of this planet, but its potential custodians, its protectors. This shift in perspective demands that we transcend our terrestrial squabbles and embrace a collective destiny, seeing ourselves as part of something far larger than any single nation or generation. The very existence of the asteroid threat forces us to think on timescales that dwarf human lifespans and political cycles. We are compelled to contemplate civilizational and geological timescales to plan not just for the next 5 years or even the next 50, but for centuries, for millennia into the future. It is a challenge that demands a level of international cooperation and long-term planning that almost no other problem has yet managed to inspire. National borders, economic rivalries, and ideological differences shrink into insignificance when confronted with the shared, universal threat of an object weighing billions of tons, traveling at speeds exceeding 40,000 kilometers per hour, on a collision course with our shared home. This truly is the ultimate tragedy of the commons problem, but amplified to a planetary level. The Earth, our singular oasis in the vastness of space, is a common resource, shared by all life. Its protection is a collective responsibility, and failure means the irreversible loss of not only our shared home, but also all its future potential, all the untold stories, all the scientific breakthroughs, all the artistic creations yet to be born. The stakes could not possibly be higher, demanding a unity of purpose that remains elusive in so many other aspects of our modern world. So, we are left to ponder a powerful, indeed, a haunting question. Is humanity merely a fleeting fever, a brief, chaotic biological spike on the surface of planet Earth, destined to be wiped out by the next great impact, just as countless species before us have been? Or are we, through our ingenuity, our foresight, and our growing capacity for global cooperation, becoming something far more profound? Are we evolving into the nascent immune system of the biosphere, the very first line of defense, capable of protecting not only ourselves, but all life on Earth from the random, brutal violence of the cosmos? The reality of killer asteroids, therefore, is not just a threat to be meticulously managed by engineers and astronomers. It is a powerful, inescapable mirror, reflecting our own maturity, our foresight, and our ultimate place and purpose within the vast, indifferent expanse of the universe itself.